Ever look up at the night sky and just think, like, whoa, why is everything spinning?
It is pretty wild when you think about it.
It's like the planets, the stars, even those giant galaxies, they're all swirling around out there. It's like a cosmic carnival ride or something.
It's true. And the craziest part is it's not random at all.
So today's deep dive, we're tackling the science of spin. And guess what? It all starts with the Big Bang.
It all goes back to that, yep. And the key to it all is this really cool concept in physics, angular momentum.
Okay, so angular momentum, break it down for me.
So angular momentum, it's like a fundamental rule that the universe has to follow. It's what makes a figure skater spin faster when they pull their arms in.
Right.
It's that same force acting all across the universe, influencing how things rotate. Now picture the Big Bang, right?
Okay, I'm picturing it.
But instead of this perfectly smooth explosion, imagine it's more like, if you dropped a giant sack of flour in space, it's gonna be lumpy.
Yeah, definitely not smooth.
Exactly. You got these denser areas all mixed in with less dense areas and those little imperfections. That's where it all begins. Those are key.
So you're telling me those clumps, even way back then, they already had a little bit of spin.
Precisely. And those denser spots, they're like gravity's VIP lounge. They've got more pull, more matter gets drawn in, and as it all spirals inward, the spin gets faster. Just like our figure skater, only now we're talking huge clouds of gas and dust, the stuff that galaxies are made of.
Whoa, I'm talking about things as mind-blowingly huge as the Great Attractor, right?
Right.
That thing is massive. It's a wall of galaxies stretching across like hundreds of millions of light years.
It's gigantic.
Are you saying that even something on that scale got its spin from these initial tiny cosmic clumps?
That's exactly what we think. And it really throws into sharp relief how important these early imbalances were. It's like they set the stage for the entire structure of the universe, these superclusters, these vast cosmic voids, all because of those tiny differences in the beginning.
Wild, right? It's like a cosmic game of billiards, where the Big Bang took the first shot.
That's a great way to put it.
And we're still seeing the universe react to it billions of years later.
Exactly.
But this spin, it's not like it stopped with galaxies, right?
You're on the right track. Think of it like a cosmic inheritance. This spin, it gets passed down. From those massive structures to the galaxies forming within them, then to each star and planet.
It's like a family resemblance, but for physics.
Yeah, exactly.
And speaking of families, our own solar system is a perfect example. The sun spins, most of the planets orbit in basically the same direction, their moons follow along.
Yeah.
Talk about cosmic choreography.
A well-choreographed cosmic ballet, exactly. And it all ties back to that initial spin. It really drives home this point of everything being connected,
It's pretty amazing.
But of course, in every family, you have those that like to do their own thing.
Oh yeah, you're talking about Uranus, the planet that spins on its side.
Uranus, our cosmic oddball.
That's like it missed the memo about spinning upright.
Right. It really is a mystery. It's possible that way back when, a huge collision, maybe with another planet-sized object, knocked it off its axis.
Poor Uranus. Rough childhood. But hey, at least it keeps things interesting. Now what about black holes? We've talked about planets, stars. What about those super dense objects? What's their spin story?
Black holes are fascinating because they're like the ultimate inheritors of this spin. You see, stars are like giant fusion reactors, right? They're constantly fusing hydrogen into helium. But when they run out of that fuel...
The party's over.
Yeah, it's like, show's over, folks. They collapse in on themselves, and when that happens, their spin goes into overdrive.
Wait, so you're saying as a star collapses, it actually spins faster? Why does that happen?
Think about that figure skater again. They pull their arms in, they spin faster, right? It's that conservation of angular momentum. Smaller object, same amount of spin energy, means faster rotation. Now imagine that on a star-sized scale. When a star collapses into a black hole, all that spin is concentrated into this incredibly tiny space. We're talking spins so fast they can get close to the speed of light.
That's bonkers. So next time I see a basketball spinning on someone's finger, or I look up at the stars, I'll remember. That's not just random spin, that's a little piece of the Big Bang, still going.
Exactly. It's a direct line from that very first moment to what we see today. And it really makes you wonder.
Whoa.
Well, if everything got its spin from the Big Bang, does the universe itself, like on the biggest scale imaginable, have a spin?
Whoa.
What would that even look like? That's a question we're still trying to answer.
That's a pretty wild thought to end on.
Yeah.
Seems like the more we learn, the more questions pop up.
That's the universe for you. Never a dull moment.
Thanks for joining me on this deep dive into the spin of the cosmos. Until next time, Keep looking up.
And keep those questions coming.